Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
How are you all doing? Welcome to another episode of Ask Us Anything about Electrochemistry. And if you notice that we just that just quick promo for the Electrochemistry podcast, if you notice something, the dates for that is it was December 7th, which was yesterday for early access.
Hey, we're the Try Guys. They're going to see how much.
So now the Electrochemistry podcast, the first two episodes are available to our tier 2 YouTube members. So you can listen to the first two episodes of the podcast right now if you want to. It's on our YouTube channel. And so we're super excited about that. If you don't want to listen to it now, we have a public release January 4th, and that will happen. That'll be on any, Spotify and Apple and Google, however you like to listen to your podcasts. That podcast will be out. So that's something that Neil and I have been working on for quite a while, and we're super excited to share it with you. But as it is for now, we're hosting Ask Us Anything about Electrochemistry, a live stream where both myself and Neil will answer or try to answer as many questions as we can about electrochemistry, because electrochemistry is a very complex subject, and a lot of people have a lot of confusion about concepts and topics, and really this is just to help answer those types of questions. Yesterday, Neil also gave a webinar on the rotating ring disc electrode, and so if you're coming to us from there, welcome. If you're new, and then this is also a space where if you've talked to us either on the phone or through email, webinars, YouTube channels, just any questions, this is the space where we can go into a little bit more detail about answering those questions. Now, this is over 30 episodes of doing this, we have found that the questions that where you'll get the most value from us answering your questions is when your questions are not ultra specific, like what is the specific capacity of this very special sodium ion battery under very specific conditions. It's like, okay, we don't know those very, very specific answers. And similarly, if you have a super broad question like explain cyclic voltammetry or explain all of EIS, we probably can't help you that much. there. But if you have a question somewhere in between where there's a concept that you're having a hard time understanding or wrapping your head around, that's something that we can actually help you the most with. So type your questions into the chat and we'll hopefully be able to answer them as soon as possible. I'm just going through the boilerplate of all the things that we usually say. This live stream usually lasts for about 2 hours. And if you're listening to this live stream after it's gone live and it's just on our YouTube channel, we will have in a few days timestamps in the description so you can get to the specific question that you were interested in. We will try to, we are on Restream as the broadcasting platform, but we are on, you can watch this on YouTube, on Twitter. And so ask us questions on either of those platforms. But if you are a tier 1 or tier 2 member, you can join us on Restream and actually kind of take a seat and show us your data to really get our opinion or view on certain things. If you want to show us data.
Well, you can take a seat digitally.
Digitally, yeah.
If you come to our building, we're not going to let you in.
That's
the
also
the front door is locked. Please leave us alone. Okay. I'm just kidding, by the way. In case the dry sense of humor didn't translate. I'm kidding. Yes, of course. Please, if you want to, we've had a couple people. It hasn't been too many. Take us up on this amazing once in a lifetime opportunity, or many times in a lifetime, because it's like every week. But you're welcome to come join us and air your grievances about research, life, and all kinds of things. So yeah, please do so if you'd like.
Yes.
So.
All right.
So yeah, let me get to this actually first.
Yep.
So yesterday I'll basically just repeat what Alex said, but I ran a webinar yesterday, 2 time slots on RDE, Tafel, Kentucky Levitch, all that kind of stuff yesterday. Thank you to anybody who's watching now or after the fact who joined me, and thank you for those who will join me next week. It's just a 2-part one, and next week I'm doing all this data analysis. So I hope that you'll join me next week on that. And as I had promised yesterday in the first time slot, there were a lot of questions and I got to as many as I could. There was one I think that I did notice I hadn't answered, or didn't quite have enough time to get to. So I wanted to just touch on this very briefly. It was from Alfie. And I just put RRD webinar to remind myself mostly that this is where this question came from. And the question was that in case of Tafel plot, especially for oxygen reduction reaction, how do we define overpotential? And then talking about comparing 2 catalysts with different onset potentials. So I wanted to talk very briefly about this. I'm not going to talk, it's not going to be too long, and then we will get to your questions for those of you who are here now at the live stream, of course. But I wanted to honor this, what I had said yesterday. So for example, an oxygen reduction reaction, if you're looking at voltammogram, for example, you have E and I, or I and V, whatever. Typically, oxygen reduction reaction is something where you have, let me just sort of label the axis here, right? So this is like 0, okay? We're looking for a reduction reaction. And so we have, it decreases, and then depending on our rotation rate, it will flatten out, something like that, right? And the onset potential is basically wherever it starts to dip down. Now you can see it's sort of, is it here? Is it here? Is it, it's hard to know exactly where does it start dipping down. There's a little bit of subjectiveness there, right? But the point is basically wherever effectively, if we just pick a point, right? This is just call this overpotential 1 or something like that. And then you might try a different ORR electrocatalyst, and it has a curve like this, right? I'm just going to draw them mostly coinciding. And so it's onset potential, overpotential, whatever you want to label it as. I'm sort of arbitrarily doing this, might be over here. Okay, so now, first of all, just the first comments, I basically have kind of 2 main things to mention about this. By the way, I'm sharing my screen, right? Okay,
yeah.
Thank you for clarifying.
I made sure I adjusted.
The first is that generally speaking, the job of a researcher doing ORR is to find a catalyst that does ORR well. That's rather obvious, but what are the metrics for how well it does? Well, effectively like 2 things, right? How much current is it generating for the oxygen reduction reaction? And that's related to whether it's a 4-electron, 2-electron, how efficient it is, and all of that. The other is that what its onset potential is, because basically the red is better than the blue in what you're seeing here, right? So this is basically that the onset potential, the overpotential, whatever you want to call it, is less for the red one, whatever that would be, than the blue one, because it takes more voltage. I have to scan more negatively to get the blue catalyst to start reducing. That's bad. That's more energy, right? I have to polarize it more. So this would be like, for example, if you're doing platinum, the red one's platinum, and at whatever potential this happens to be, it starts reducing oxygen. But like glassy carbon, these are like extreme examples. Like glassy carbon barely does oxygen reduction at all. It's terrible catalyst. That's why it's a good substrate, because it kind of doesn't do anything or get in the way. But if you were to just do oxygen reduction on glassy carbon, eventually it will do something, right? If you scan far enough negatively, but you might need like 400 millivolts more potential before it starts dipping down and doing oxygen reduction reaction. So it has a higher overpotential, right? So just to the point of the comment that was like comparing two catalysts with different onset potentials, that's kind of what the deal is, right? And then the second thing is that how do you define overpotential? Well, the overpotential is the difference between whatever the E0. So you might have, in theory, let's say this right here is the theoretical E0. That's 0, and then I have ORR. So not to confuse 0 with O. So that's the E0 of the ORR. And so the overpotential for 1, the red, is this, this distance. I should have drawn it red. Right. So the overpotential for the red catalyst is this, whatever that number is, right? However many millivolts that is. And the overpotential for 2 is whatever this is, right? So overpotential 2 is greater, and that's bad. So you're comparing that. But overpotential is just the difference, right? Overpotential is equal to E minus E naught. So it's just the difference. And like some people put, I think usually they put it up top. I probably should have had it at superscript. So you see it superscripted or subscripted, but the point is the same, right? It's the difference between the potential you're applying. And in this case, if I'm talking about like, you might say like E onset, whatever, right? So we're talking about like the onset overpotential, but it could be any potential in this case, right? It's that difference. And so this E0 for ORR is just some number. It's just some number, right? Whatever the value is that is associated with the redox reaction. Words are hard sometimes that you're studying, right? And so for oxygen reduction reaction, it's just some number. And so whatever the potential of your onset is for your catalyst, then that's what it is. And then the difference between those two is the overpotential. So that's all I'm going to say about that. I hope that's clear enough for you. And I hope that perhaps if you end up watching this, that there's the answer to your question. Maybe it's also helpful to anybody else who's doing some ORR stuff.
Very good.
And then there was another question that happened actually earlier, like an hour ago, from Sumita, which was that, is there any relation between solution resistance and impedance and IR drop in galvanostatic charge discharge? Well, yeah. So the solution resistance, generally speaking, is the IR drop, whether it's in galvanostatic charge discharge or CV or LSV or NEV. It is that those are, you're saying the same thing. So if you're doing like impedance and that leading resistor that you get, right, that's the IR drop. You know, and it's not just the solution resistance, right? It might be a handful of other things, but that's probably the most, I don't know, significant contributing factor to it. So yes, there is a relation to it. It's the same thing. Yeah, basically. So there you go.
Yes. All right. So we have a question from Peter. Hi, are there any considerations for picking a reference electrode when testing an oxygen reduction catalyst with rotating disc electrodes to working? Any best recommendations? Also, one, thanks and happy Hanukkah. Yes, last night was the first night of Hanukkah.
Yes, it was.
So thank you. Let's see, any conditions. Really, remember, I guess I always like to say this a lot. The important things about reference electrodes is that they're they're stable
Stable.
during the length of the experiment, that the potential doesn't shift around or
Are you going to
drift.
talk about the Nernst equation again?
I could always talk about the Nernst equation. It has to have Nernstian behavior.
That's right. It's
so it has
always
to
about
obey the
Nernst
Nernst equation.
Nernst equation is Alex's favorite thing.
It is
Please
my favorite
ask
thing.
questions about the Nernst equation because Alex loves it. I'm actually not kidding.
I love
If
the
I
Nernst-
were to trigger Alex, I'd tell you to ask questions about inductive loops or what was the other thing you told me recently? Anyway, we don't have to talk about this now.
about my trigger points.
Yeah, there was something else that I'm forgetting.
Um,
But anyway, I'm totally derailing this live stream. I'm sorry.
Exchange current density.
Yeah, that was another
Exchange
one.
current density is
Yeah,
another
yeah.
one, which is funny because that's what you talked about.
Yeah, I talked
yesterday
about
at
it
the
yesterday. I actually forgot about that. I should have been more sensitive to your needs. I'm so sorry.
No, it's okay. It's just letting people know that like you don't need to talk about exchange current density. Just talk about the heterogeneous rate constant. It's a better indicator of.
Yeah, but you can get the exchange current density from your Tafel plot.
Yeah, but you can have a really, really high exchange current density if your area of the electrode is super big.
That's true.
The heterogeneous
It's
rate
true.
constant takes care of that.
That's true.
But to answer your question, it's going to depend on the electrolyte that you're doing the oxygen reduction reaction on in a rotating disc. Most of these, I believe, are aqueous. So use an aqueous reference electrode. I like silver chloride personally, but and if you have a chloride ion as the electrolyte, as just part of the electrolyte, that's even better. You want to have a common ion if you can help it. That's my 2 cents with regard to there's nothing as long as it doesn't create contamination in your system. If you're worried about chloride ion contamination, or you need to use like a calomel, or if your lab doesn't want to use mercury, sometimes it's even just price. Like, silver chloride is relatively inexpensive. You're going to use something like calomel is more expensive. Double junction reference electrodes are more expensive. So that's another thing. But yeah, stable Nernstian fast electron transfer kinetics that govern the reaction, and that's my 2 cents.
That's good. It's good 2 cents.
2 cents.
I also want to mention, because I think we forgot, we talked about this. And then, so at the end of this live stream,
right,
we are going to play a couple of minutes from our first podcast episode as a special sneak preview, sneak peek, sneak whatever.
Yeah.
So for those who are tier 2 members, you can listen to it over the next month, over the next month. And then like Alex said, in January, it'll be available to everybody. But just as a little teaser, we're going to play the first couple minutes of our first podcast episode. Again, it's available right now on our YouTube channel for members. So look forward to that at the end of the live stream today.
Yeah. Yes, that's right.
Okay, let's see. Reference electrode. Okay, so Sage or Saga? I think I read it as Sage, ends. But it's the Saga ends. Okay. So asked, what is the specific capacity of acetylene black as which is used as a conducting medium for electrode fabrication? So I asked basically to clarify, was assuming that they meant the specific capacity as like a battery material, and they said yes. So what I will do is briefly show you this calculation. So basically, this is something that's where's my screen share? So this is something that is done for battery folks in battery materials. So the answer I think is 372 milliamp hours per gram. Okay. So here's where I'm just going to fully admit that I don't 100% know. Acetylene black is just carbon. Like X black usually means it's like carbon, just graphite that was prepared from some material, right? Okay. So like you'll have carbon black, acetylene black. There's others. I know there's others, and it's been a while. I'm not in graduate school anymore. But so you may correct me if I'm wrong, and I'm not 100% sure. So the calculation I'm going to show you could be applicable, and it's where you get this number for any other material. So if the material and its formula weight is different than what I'm showing you, you just use something different, and that's all you have to do. Okay. So this is actually like one of the simplest calculations in the world. When I learned this, I was like, my mind was blown. It's like the specific capacity of battery material. So for example, this is what's used in most lithium ion batteries as the anode is carbon. Cathode materials usually have 100 to 150 milliamp hours per gram. It's one of the reasons why people are constantly looking at things like silicon and tin, for example, because they have a theoretical capacity of like 4,000 milliamp hours per gram. And you might say, well, that's terrific. And I'm not going to talk about, unless there's questions about it, I can, but there's other reasons why that's not great and they're not used as often. But where do these numbers come from? It's actually an extremely simple calculation. Okay. So again, I'm assuming acetylene black is carbon. Okay. And the carbon that is its form as an anode material for lithium ion batteries it's C6. There's basically six of them, right? So the molecular weight of carbon is 12, right? 12 grams per mole. And there's 6 of them, right? So that's 72 grams per mole. Okay, so this number comes from the inverse of the molecular weight. I'm going to repeat that. This number right here is the inverse of the molecular weight. That's it. That's all it is. But please explain. I'd be happy to. Okay, so 1 over 72. This is literally just dimensional analysis, okay? This is the formula weight of C6. It's 172 grams per mole, 1 over 72. Now I'm going to do stoichiometry. So the equation basically is something like Li. I'm doing lithium, of course, that's my specialty. But similar analyses could be done if it's sodium or zinc, probably. But lithium plus I guess 6C or C6, whatever, plus an electron goes to LiC6, something like that. Okay. So it's a 1 electron process. Okay. So the next factor is mole of carbon or I guess C6, right? So this is grams of C6 per mole of C6. Now I'm just using stoichiometry. So there is 1 mole of 6C or C6, whatever, it's the same thing, per 1 mole of electrons transferred, right? I'm just using the ratio from up here. So it's just multiplying by 1, but technically I need moles of electrons, not moles of C6. Okay. Now I use Faraday's constant, 96,485.3. If I don't know that number off the top of my head, I'm immediately fired as an electrochemist. Coulombs per mole of electrons. Let's see, what else am I missing here? All right, coulombs. I need 1 amp is a coulomb per second. So I'll put the seconds up here, right? That's just a unit conversion, right? 1 amp is a coulomb per second. Okay. And then I have the last one. Sorry, I'm kind of running out of space here. There are 3,600 seconds in 1 hour. That's it. Let's do some math. Okay. I don't think I can show the calculator. I'll have to share it, right? I'm going to plug this into my calculator and then you can independently do it. But I hope this is right. I'm pretty sure I'm right. So let me double check. 1 over 72 times 96,485.3 divided by 3,600. Yeah. So it equals, I know you can't see the calculator because it's whatever, but I get 3722. So it's this calculation equals 0.372, and it's like there's some decimals or whatever. But look at the unit, right? Okay. Moles of C6 goes away. Okay. Moles of electrons goes away. Coulombs goes away. Seconds goes away. What's left? Amp hour per gram. So 372. So if I just multiply by 1,000, I can get milli. 372 milliamp times hour divided by grams. Milliamp hours per gram. That's it. That's the calculation for capacity. It's literally 1 over the molecular weight. That's it. It's such a fancy, crazy thing, and that's quite literally how you get it. So the last thing I'll say is that if acetylene black isn't exactly this, it's not C6 in its form of what the material it is, then if it's C6 H33O1, uranium 12, whatever that formula weight is, just do the same calculation. That's certainly not what it is. I'm just teasing. Okay. But that's it. That's literally how like specific capacity is calculated. It's just the inverse of the molecular weight with all of those fancy transformations. So there you go.
Wow, that seems like every molecule undergoes like an electron transfer.
Oh yeah, every single one.
Super-
Yeah, that's why it's called theoretical capacity. So in reality, your benchmark is how close to 372 am I getting?
Yeah.
When I put my battery together with carbon and whatever, and you never get exactly 372. You get close, or
you actually do get close.
Yeah, you get close.
Wow.
Oh, for sure.
I'd figure there'd actually be some pockets of carbon and lithium and all
that can happen, but not. That's why carbon's so good. It's actually tends to be quite good, and the efficiency of batteries is very, very high. So you do tend to get a decently close, depending on. There's things like structure. It's actually, now I'm going off on a battery tangent, but basically, batteries follow a counterintuitive kind of phenomenon to like regular carbonaceous electrodes, which is where you're trying to do nanomaterials and make the surface area as high as possible. You go in the exact opposite direction. You need a very, very low specific surface area for it to behave properly.
Interesting.
So like carbon battery materials behave horribly if they have a very high specific surface area. You want them to be as small specific surface area as possible. So
like would glassy carbon be a good?
No, it's not porous enough.
Okay, so it still needs to be porous, but not so porous that
something like that.
Okay, so it is
like if you do BET analysis on something like Vulcan carbon or some other carbon materials that are used for fuel cells, they have like, I'm just throwing this out there, I'm probably off by a bit, but like 1 to 200 square meters per gram, something like that. Really high surface area. Right. Battery materials, it's like 2. There's one called Super P. I think it has like 5 square meters per gram or like 2 square meters. It's really small.
Okay.
Like half a square meter per gram. It's like orders of magnitude smaller.
Yeah.
Because if you have too high surface area, you get all SEI. All the surface area, you just get SEI, and you get no intercalation. You get no storage.
Okay.
It's just SEI.
Okay.
Which is a secondary form of storage that's not stable.
Stable needs to be stable.
Yeah. So there's all these different kinds of battery tidbits here, I guess. So there you go. That's how you calculate specific capacity. So take that. If you have any other follow-ups, Saga ends about that, let me know. If it's a different type of material you're talking about, or I might be misunderstanding, but that is effectively how you do it.
All right, we have a question from Adil. Thanks for waiting. Hi, sir. Can you explain the electrochemical sensing, and also if the electrode deposition is done with the DC advice, does it really work? He's following up to say that he's a master's student and doing electrochemical sensing and is just starting off. So electrochemical sensing, very simply, it's an analytical chemistry technique where you're using electrochemistry as a sensor. Oh God, I really explained.
I love the circular definition.
Yeah, the circular definition. Yeah.
That was excellent. As you're saying it, your face is like, "Oh, what am I doing?
What am I doing? I'm just saying that electrochemical sensing is when you're sensing electrochemical."
But it is.
That's
what it is.
It is true.
Yeah.
But in electrochemistry, and Neil actually put this quite well yesterday. There's like 3 variables in a way. There's current, voltage, and time. And electrochemically, we can measure things. We can measure potentials. We can apply potentials. We can measure currents. We can apply currents. We can extrapolate currents to give us things like charge. And we know things like the number of, just what he was explaining with specific capacity, that there's so many coulombs of charge per mole of a given thing. And so if you're sensing something, you're trying to figure out how much of a given thing there is, detecting quantitatively. So electrochemical sensing utilizes, it's going to utilize either a form of voltammetry or a thing where you measure the current for that is the response of a specific analyte that you're interested in. So electrochemical sensors, the most common one, most popular, is a glucose sensor for people who have diabetes and they need to test their blood glucose level. And glucose by itself is not electrochemically active, but glucose is in equilibrium with, I believe, glucose oxidase or a type of enzyme.
Isn't it? Is it?
It's in equilibrium with.
That's the
enzyme,
right?
That's the enzyme.
Yeah, it makes something.
It makes something.
It makes something. We should probably know this because we have a lab about this, but
Yeah.
It makes a species that is electrochemically
active.
Yeah, something like that.
Yeah, so it makes this electrochemically active species in equilibrium. And
is it just peroxide or something?
Well, when you use glucose oxidase,
it decomposes glucose.
Decomposes glucose and forms peroxide, and you can detect peroxide electrochemically on a platinum electrode. You can oxidize. It undergoes a reaction.
You can
reduce the I think we've had numerous discussions. Like, do you oxidize peroxide or do you reduce peroxide?
I think anyway.
And you can do to a degree. I think you can actually kind of do either one. It depends on the pH of the solution. Is really the pH of the solution will govern that.
Anyway, you can detect it. Yeah.
You can detect them, and so a lot of people just just very simply, if you have, I'm just gonna share. Where is my PowerPoint? Here we go. So, all right. So if you have, we know that, if you have some molecule and it's A, plus an electron, it's in equilibrium to give you B. We know that A is an electroactive species, but maybe A only works on some kind of copper, copper oxide or some special thing. Well, you can develop a sensor that has this copper oxide, and that's the sensor material. And copper usually maybe a little orange or something like that. It has kind of this color ish. And then when you're and that's on an electrode. And so when you have some A in solution, it's just kind of floating around, you have a lot of A, but if you apply a potential to your copper electrode or copper oxide electrode, and A then goes to B, you'll get a voltammetric response. So it can be in many different forms, and this is what a lot of the research is about. So maybe you do a chronoamp experiment, you have time, you have current, you apply a step potential, and then you get this kind of exponential decay as part of your result. The Cottrell equation governs this, and so you can actually do some quantitative analysis and get do a quick calculation, figure out the area under the curve. You get coulombs, and those coulombs can be converted to the number of moles of A. And so this is a way you can electrochemically sense how much A is in solution, because the concentration of A is proportional to the current that you measure. And so the challenge, as a master's student, what your challenge is most of the time is figuring out what is the thing that does the sensing that's specific, that's a selectivity thing. There may be a lot of, some things may be electroactive, but they're not sensitive to certain materials. So you may have to develop what is the sensing platform that you're going to work with. And then you need to discover, okay, how can I detect it electrochemically? Do you do something like chronoamperometry? Do you do cyclic voltammetry? Maybe there are a very specific set of parameters in your electrochemistry experiment that actually give you an accurate response. And in what situations are you sensing it? Are you sensing it in a traditional electrochemical system, or is it something like out in the field? Like, I want to test for a drug that's in your water. Well, it's not going to be salt water. It may be contaminated. Can you make this thing robust and selective? So these are like the challenges that I've talked to people and have seen that people who deal with electrochemical sensing. Now, with regard to electrodeposition, you absolutely can do electrodeposition with a DC device. And how this works, generally speaking, most electrodeposition, from my experience, is the deposition of some kind of metal, like electroplating. So you reduce. So most metals in solution are cations. They're positively charged, and you want to reduce them to a solid metal that's on the electrode surface. So a lot of the times you'll buy a salt of your metal of interest. It's in the positive, it's in the cationic state. You apply a specific reducing potential, and you reduce the metal to the neutral form on the surface. So that's kind of in general how electroplating and electrode deposition works. And you'll observe a current associated with that process, and you can relate how much of the metal did you actually deposit on your sample based on the current response that you get. So actually very similar to like the chronoamp type of experiments. But a lot of people do other physical, mechanical things like stirring a solution to affect how the deposition actually occurs. So hopefully, Adil, that kind of gives you a general idea about how electrochemical sensing works and how electrode deposition works in a way.
In a good way, I would say.
Hopefully in a good way.
Very good way.
I am keeping an eye on Twitter, and so far there aren't any questions. But thanks for those of you who are retweeting or re-Xing. I don't know, Twitter X.
Re-Xing.
Re-Xing.
Sounds like they're breaking up with us.
Yeah, that's right.
You know?
Again.
Like, I X'd you last week.
Yeah.
Now I'm Xing you again. So if they X'd us, but then they X us, two wrongs make a right.
That's right.
Right? So now they're back with us.
Yeah, they're back with
That's
us.
right. That's how math works.
Yeah, so we need at least two re-X's to be
every even numbered X we get on Twitter is a new relationship blooming.
Yeah. Well, it looks like right now there aren't any questions. We can still hang on as we usually try to do this for 2 hours. But of course, if there's no questions, we can end early. But in general, one thing to keep in mind, it's December, it's the holiday season in the United States. And so over the next few weeks, we may not have as many live streams. I think next week we actually have a potluck for Pine Research. And it's like, oh, that's like the same time that we normally run these live streams. So so we might not be able, we probably can't do it unless, because that would annoy our boss.
Generally like our colleagues more than people on the internet. So logistically, we're probably not going to be able to do our live stream next week in all seriousness, unless we did it earlier in the day. Maybe we could do it earlier.
Oh, we can always
I don't know if that's going to throw people for a loop, you know?
Yeah.
I think folks in Asia and in Europe might appreciate it early. Maybe we could do it earlier. We'll think about it.
We'll think about it.
Check our YouTube channel.
Mm-hmm.
And we may not be able to for one reason or another. But if we can, we may perhaps do it earlier in the day, and it will likely not be at this time next week because we do have a company function and we can't interrupt that. But after that, as Alex said, I will be probably out for the rest of the year after next week. And you may or may not be as well. So, or it'll be spotty probably until January.
Yeah.
Here, as is typical, I'm sure, and I hope many of you get some time to enjoy, holidays or break time with your loved ones too. So that's a good thing to do.
Yeah, absolutely. You don't have to do electrochemistry all the time.
Well, unless you have a really crazy advisor, I guess maybe then you do.
Yeah, then you do,
because that does tend to happen.
Or you're us, and we do electrochemistry all the time. Think about this stuff all the time.
All the time. Even when I'm at home and I'm with family and we're celebrating the holidays, all I'm thinking about is batteries. And solar cells. It's just always there,
Yeah. Looks like Peter has another follow-up. Not a stupid question,
there's no
but
stupid
one
questions.
maybe stupid following question. If I choose the silver chloride reference electrode, should I correct the results with the difference between that and the standard hydrogen electrode using a potentiostat?
It's up to you
for the above. Yeah, I mean, you can always test to see how accurate your silver chloride reference electrode is by basically doing OCP, open circuit potential, with your potentiostat, with a silver chloride reference electrode and a standard hydrogen electrode. If you have both of those electrodes, put them in a conductive solution and then measure the open circuit potential, then you'll get what the potential difference is. And if you compare that to literature and you find that like it's off by a lot, then you have an issue. But if it's within a few, like I would say at least 5 millivolts or so, you're probably fine.
Yeah. And I mean, I guess the other thing too is that like whether you want to correct it for when you publish your paper, right, or you give your presentation, it's totally up to you. Like,
yeah,
I think there are some like electrochemists who are very adamant about publishing versus NHE or SHE, whatever. You know what I mean? They'll convert everything. I never did that.
Yeah.
I like it. It doesn't, like, to me, it's so completely irrelevant and arbitrary, because if you're looking at a paper and someone reported a voltammogram or whatever, and it's the x-axis is volts versus AgCl, big whoop. If anybody wants to know what it is versus NHE, they can just shift it 200 in their brain, you know, you know what I mean? It's actually quite arbitrary in my opinion. Some people might have a more militant, you know, kind of opinion about it. Yeah. Some people do have, fine. Maybe they have their reasons. I don't find it to be of tremendous consequence. The only real, you know, considerations are for you, in my opinion, comparing all of your data against itself, right? If you happen to have some tests with different reference electrodes, then maybe it makes sense to convert everything to one reference, you know, and then convert everything to NHE. And, you know, I will admit that, okay, for perhaps by correcting everything to NHE or SHE, whatever, before you publish, makes it, let's just say, easier for anyone reading your paper to compare. In some, if they have a different reference electrode, everybody reverts back to the, you know, 0 volt standard. Okay, fine, maybe, but there's nothing intrinsically wrong about publishing data, for example, versus SCE, CalML versus HGO, you know, whatever. It happens all the time. So to a certain extent, it's really up to you. And you can do it with a potentiostat. Some potentiostat softwares allow you to, like, you know, shift axes. You can also just do it in, you know, your spreadsheet afterwards. Like there's no protocol here. You do it however you want, because all it does is move the entire CV or whatever left and right. That's all it does. You know, it's not real mystical, so to speak. It's just moving the axis left and right.
I think one person I remember, everyone is again militant, but one thing that I think is, one person has at least the view or the opinion, like, you should report the electrode that you used in the publication. So sometimes it can be like, you may write in some small text somewhere like, oh, we use this electrode, but then when you have it versus a different electrode throughout all the experiments, it could maybe throw a few people off for a loop. But I think, like, report what you did.
I think that's a good point, because if you report versus SCE or whatever, they know you used SCE. And then at least it gives them information as you're reading that CalML is what was used, which, I mean, you could always discern from the experimental section anyway. But it's like, looking at the plots, by putting the reference electrode you actually used, it does give the reader more information. So I think that's a good point. Looks like Tafara, I think Tafara joined us last week or the week before, so I recognize the name. Let's see, there's a new question here saying, reading this on the fly, so let's see here. Testing R-amine as a potential lithium-ion battery additive to improve safety. When we add them to the electrolyte and we do impedance studies, conductivity nearly triples compared to the blank electrolytes. But when we build the actual lithium-ion battery cell with it, the voltage drops from 3.4 to 2.8. Do you know what might be causing this? R-amines were fully dry and synthesized in an oxygen-free environment. So
think about this.
Let me think for a second. You've improved the conductivity of your electrolyte,
but they observe a higher voltage drop,
a big voltage drop,
which would suggest that the resistance is higher when they use these amines.
Yeah, I mean, unless the voltage drop is from something else, but yeah,
Yeah.
fundamentally, right? If you have a drop in the voltage, V is IR. So
Mhm.
as R goes up for any set conditions, V goes, the drop, it's like a higher resistance. But if your
Yeah.
conductivity is going up, your resistance should be dropping. So this seems counterintuitive, I think, is the kind of the point.
So one question for Tafara is, you said that you did EIS studies where you observed the triple point, but then you also, when you built the actual battery, that suggests that the EIS studies were not done on the battery.
Yeah, it looks like you're doing
Like you did
EIS,
two different experiments
like you're
for two different
just.
systems.
It seems like they've done impedance studies on blank electrolyte and impedance study. So I guess my first question is, how are you calculating conductivity via impedance on both the blank electrolyte
Mm-hmm.
and the added electrolyte? Are you doing just like a very short impedance test and taking the high frequency intercept? What are your electrodes that you're using?
Yeah.
Are you sure that the conductivities you are measuring in these tests, are you sure that those tests are not convoluted by any or confounded by anything? So for example, doing your impedance test on just the battery electrolyte itself can present some problems. It's battery electrolytes are also intrinsically not the most conductive anyway. So I would hope, consider the EIS test you're doing on the electrolytes first. Is that procedure sound? Maybe it is. but that's the first thing that comes to mind. Consider that, and maybe it's hard to exactly type everything out, exactly how you did that. I know it's probably
So
a bit much to type. Yeah, just the electrolyte, right? So you're basically testing just the electrolyte, but you must be using electrodes to do so. So you're just putting 2 platinum wires in solution or something. Like, you have to be using some, I assume, electrodes, right? If you're getting the conductivity. So, there's some ways to do that. For example, with like a Lugin cell, you can do that by taking a very short cyclical tamagram and assuming that it's linear and using Ohm's law to get the R. You can just do impedance, and generally speaking, it's like the high frequency. But again, high frequency can be tricky if you're using a reference. If you're not using a reference, if it's not that conductive, you might have some artifacts at the higher frequency. You might have some inductance from cabling. There's some things that can confound these things. So I guess fundamentally, 2 platinum wires. Yeah. So yeah, I wonder how, and how repeatable, how reproducible is this? There's just some questions, because I would also consider what impedance looks like on the actual battery.
Yeah.
And part of this as well could be that the construction of a battery. So if you're making a coin cell, there's also a lot of steps involved in making a coin cell that can go wrong, or if that isn't perfectly consistent, you might have a drop in voltage that's related to other things and not the electrolyte. You might think to yourself, I made these 2 batteries and the only difference is that I had an additive in one electrolyte compared to the other, but there's something else not that is unbeknownst, to you. There might be something that is a little less obvious, but electrochemistry is sort of famous for the phenomenon that you do 2 things the exact same, or you think you get different results, but it wasn't the exact same for one of a few different reasons. That happens quite often.
Insanity is doing the same thing twice and expecting a different result. Science is doing the same thing twice and getting a different result.
And science is doing the science. In science, you could actually probably word it like science insanity is doing the same thing twice and expecting the same result.
Yeah.
It's like, especially electrochemistry. I mean,
do you think that
also, well, I was just gonna say, I mean, the voltage of your cell
isn't ideal.
Well,
even for
the only other thing that comes to mind, to be honest, is that be careful. So let's say, for instance, that your platinum wire impedance test is okay, and that the conductivity is better, and so in theory it should improve things. What might be happening is the amine, right, that the voltage of your cell being 3.4 volts under whatever normal conditions, and I don't know what your anode and your cathode are. Okay, so fine. But if the amines could be adjusting or affecting the voltage of the battery because it might be interacting or interfering with either or both of the anode and the cathode themselves, right? It might not be just improving conductivity, which you would expect to improve battery performance. It might be interfering with the anode reaction. It might be participating in some way in the intercalation or the on either side or something like that. And so the voltage of a lithium ion battery is predicated on the thermodynamics of
Lithium.
the oxidation and reduction reactions on either side.
Yeah.
And so if the amines are participating in any way, maybe you don't know what that way is, it's going to change that thermodynamics and the voltage. And so that might not have anything to do with the voltage drop, from the solution conductivity, but it might be the actual thermodynamics are different entirely. And it might be related to the anode cathode reactions, or it might be related to the SEI. Because remember, when you the solid electrolyte interface that forms typically on the anode, but a little bit on the cathode too, when you construct your battery and you start cycling, that's a decomposition product of the electrolyte. It's a minor decomposition product. So adding anything different to the electrolyte is also going to probably adjust and affect the SEI in some ways, which could impact the potential difference between them. So I wouldn't. So again, it might have something to do with the measurements you're doing of the conductivity, perhaps, but assuming that isn't the problem and you have accurately compared the conductivity of both electrolyte situations, my assumption would then be that it has something to do with the thermodynamics of the battery reaction you're studying. It's impacting one or both of the anode and cathode, such that it's basically negatively impacting the cell voltage. And so you might be getting an answer that you didn't want, but it's still a scientific answer, which is that despite the improvement in conductivity, these are not appropriate electrolyte additives because they are deleterious to the cell voltage. And so, if it's any consolation, when you do stuff like this, especially in battery research, you're trying to find the next great anode, cathode, or electrolyte or additive or whatever. Sometimes it's a perfectly reasonable publication to say, impact of this terrible thing. Like, I'm serious, it's funny, but it's actually true. Like, a negative result is still a result. So if the end result is that these don't work and they're bad, that's useful information for the community. You can publish a paper that says, like, we've studied this and it isn't a great, and we're going to study these other things in the future or whatever, but that's still something the community would need to know, because someone else might have the idea to do that. And then they'll read your paper and then they'll say, oh, I shouldn't do that because this person already determined that that's not good. Right. So,
I just think of it as I agree. I also think of it from like the chemistry standpoint. Like, you may discover that these amines, and you have R, so like R could be anything, it is anything. You may actually find that, like, oh, these, R-amines are proposed as a thing that can improve the stability of lithium-ion batteries and to improve safety, but they form X or generate certain chemical bonds at the anode or the cathode, or form an inorganic complex with lithium. Like, because Neil and I have talked about like the quality of scientific papers, and so it's like, it's not, I think, instead of just saying like, oh, this thing just didn't work, it's like, well, what interesting, like, why didn't it work? Like, what's the interesting thing about it? It's like, oh, these things formed X, or we found they polymerize, or something like that. So I'm always, I push you to to try to get to the chemistry. Maybe you're an engineering student, so all this chemistry stuff doesn't matter at all. But like to get to like, okay, what's the thing that we can learn so that we can think about designing a new additive that makes
Yeah.
the electrolyte better. That's my 2 cents. Another 2 cents. We're up to 4
We're
cents.
up to 4
now.
cents.
4 cents now.
If you invest that, you're going to be super rich in 5 trillion years.
Yeah, that's right.
Sorry, that's an ultra dad joke right there. Yeah.
All right.
You know what we should do while we are waiting for other questions, or either that, or if there aren't any more, then we'll wrap it up. Maybe everybody's already on holiday break, which is fine. But I'm very disappointed that they're not in the lab all the time.
Yeah,
it's very disappointing. That's not appropriate.
And Chris isn't here. Chris Georgiou.
He's usually here, and I bet he's on holiday already as well. And I'm so disappointed in everybody.
I think he's just dealing with adult things,
enjoying
like
their lives instead of just living and breathing electrochemistry constantly. Okay, there's no success without constant electrochemistry uphill struggles. That's the secret.
Secret to life.
Secret to life.
Charlie Munger said that at some point.
Charlie Munger said a lot of funny things.
Said a lot of things.
Rip in peace.
Or Winston Churchill. I think Winston Churchill.
Yeah, Winston Churchill had a lot of quotable moments. There's a lot of like Winston Churchill quotes if you look them up. He was you never know if those are true. It's like,
oh yeah,
it's like 1940s. So it's like if some stenographer was just following him around with a pad and a paper, was like, oh, that was a cool thing you said. Like, I don't know how did they get the quote? I guess maybe he gave speeches. Maybe that's, maybe I'm overthinking this. I don't know, whatever. I just imagine like people like in the 1800s, there's a quote someone said such and such. It's like there's no that at all.
Oh yeah.
So someone would have just had to have like been walking around or like listening to a thing, just like furiously writing what the person was saying or something. I guess, right? I don't know. It always seemed funny to think about quotations from hundreds of years ago. It's like, how do we know?
Yeah, I mean, I guess like there used to be diaries, like
that's
what
true.
is it? Like Meditations by Marcus Aurelius is all.
Yeah.
It's just his diary.
Yeah,
that's it.
So it doesn't mean he said it, a book, but it means he wrote it.
Yes, that's
true. He
true.
may never have said anything.
He had a scribe. Scribes were jobs.
That's true.
Electrochemistry wasn't cutting it for you, you could be a scribe. And now AI has taken over all the scribe jobs. So yes, I'm playing Diablo. Last day of classes. Can I measure EIS by modifying an electric guitar? All right, playing Diablo. Diablo 4, I presume. I've also been playing.
Was there a new one?
Yeah, Diablo 4 came out June 6th, and it actually had a pretty rough. It's still pretty rough. It had a good launch from a technical side, like the servers didn't crash, which other ones did.
So is your gauge over whether something worked is if the servers crashed or not?
Oh, he plays 2. Oh, nice. Good man, Barry.
Diablo
2. Yeah, that's yeah. Neil's not a gamer, but I'm more of a gamer, and Diablo 2 is considered the really the pinnacle in some ways of action RPGs that really set the stage for tons of other Diablo games to come out. But yeah, Diablo 2 is fantastic, and it's like perfectly balanced in a way. But he has a very good question about, can I measure EIS by modifying an electric guitar? And this goes into Neil's
modifying electric. So an electric guitar is going to give you 6 different frequencies, my friend. That's it. Okay. So maybe you can keep retuning each string and ever so slightly change the frequency, but you're very limited on the impedance that you can apply. Oh my gosh, that's funny actually. Yeah, it's sound sine waves are something else, right? Sound moves.
Sono electrochemistry. Something like that.
And it's obviously it's sinusoidal, but sound is different because sound is a what is it? It's a compression wave, right? Sound actually moves by compressing the air and moving that way, right? It's not like a wobble up and down like the way electromagnetic waves are.
No,
sound is a compression. I'm going out of camera. I should go in camera. It's like it's a compression. That's how sound propagates. That's why sound needs a medium. That's why Alien was famous for. There's no one can hear you scream in space. No one can hear you scream because sound requires a medium to move through.
Yeah,
Because it's compressing molecules. It's a propagation of compression. That's how sound moves. So anyway, all that is to say, no, you cannot do impedance with an electric guitar. And you do have so many frets. That's true. I guess the frequency does change. So the question is, what would an impedance experiment sound like on a guitar? Would it sound like Eruption by Van Halen? I think so. That's what it would sound like. Do you know Eruption by Van Halen?
If you played it, I probably probably wouldn't know, honestly. You definitely
okay. I'm so sad. He doesn't. You're not a music person.
I might know it. I'm not so sure.
All right. I don't care. I know this is an electrochemistry thing.
Pickups convert to AC.
Eruption by Van Halen is like one of the most famous guitar. It's like a minute long. It's not long.
Okay.
I'm gonna. It's by. This is not an opinion. This is fact. The greatest guitarist of all time, Eddie Van Halen. He's the greatest guitarist ever lived. All right, hang on. I'm playing a. Is this legal? We're not allowed to do this. I can't share, right? Is that a copyright thing? I'm playing it just for you.
Okay.
He's listening to Eruption right now. I don't not know video games. I know a lot of video games. I do know a lot about music though.
And I know a lot about. I know a pretty good amount about video games and very little about music. I'm not like.
Yeah. See, I think that means that we're quite complimentary, right?
Yeah.
If there are questions about video games, Alex is your man, and if there's questions about music, I'm your man. I know a lot of things about music. In fact, I have like satellite radio in my car, and I'm constantly listening to like the '60s channel because I'm like an artificial boomer. Right? I love older music. You'll recognize this next part because it's the end of it. This is like the famous riff.
Okay.
You can't tell me you've never heard this.
I mean, I probably heard it. I just couldn't tell you like where.
Yeah. It's from 1984. Eddie Van Halen, 1978. It usually goes into Pretty Woman. They Van Halen redid Roy Orbison's song from the 1960s, Pretty Woman, and it goes into that. And Eddie Van Halen apparently just like was messing around backstage one day, just playing that. Because that's the kind of thing that he just casually was like, yeah, I'll just do this crazy thing. And he's doing it. And one of his producers or something like that walked in and was like, that's the most insane thing I've ever heard. Can we record that? And Eddie was like, sure. So yeah. I think there's actual questions.
We actually got some actual questions.
We were filibustering because there weren't any questions.
We can talk about video games and music in a minute.
I'm always down to talk about music, but let's see.
We got Umar Aziz, can you please let me know why the Dunn's model does not fit properly? In CV, some part of capacitive part is out of the diffusive. In CV, some part of the capacitive part is out of the diffusive. Why? So I'll be honest, I don't know a lot about Dunn's model. I watched a video about the Dunn's model, and I'm actually like, the way somebody described it did not make me sound like it was correct, or that it didn't make a lot of sense to me. It's like
four basic patterns of sensory processing. Is that it, or am I thinking? Is this not sensory processing Dunn's model? Is that what that is?
There's the Dunn method to calculate like diffusive and capacitive current.
Oh, I don't know
stuff like that. Okay. And I've seen like some pictures of it, and it is, I don't know, it's kind of, I don't know enough about it. It might be somewhat questionable, but what I can do, and let's just do an experiment like right now, which is let's simulate a voltammogram And I'll make this really,
Yeah,
I'll make
let
this
me hide the
kind of
question so we can see.
kind of small. Yes, thank you. So this is the voltammogram, and it's just a simple electron transfer. And I think I have the settings. Yes, so I have the ability to control the double layer capacitance. So this is the case where there's no Faraday current, and I'm going to archive this. So I have this CV. Now let's take a let's do like I think microfarad is a pretty, like 25 microfarad is pretty common. Let me see if I simulate it. Okay, it goes up. I think I want it to be a little, bit bigger, a little bit more easy to see the difference. But now if I archive this and then I do, let's see if I make a new plot, and then this is the CV results from where is my voltammogram? Here we go. So this is no. This is, I think. Okay, so this is when we have zero capacitance, and this is the voltammogram when we have quite a bit of capacitance. All right, so so this is kind of what you would observe. So the blue one represents like 100 microfarads of capacitance, which is quite big. But at the same time, there's also like, there's no solution resistance. There's no other things. Like if I add solution resistance, it would make things more complicated. And so I want you to kind of keep this picture in mind. You'll notice like at the edges right here, this is the capacitive current. And then here, there's actually, it's not that big of a difference between when you have capacitance and you don't have capacitance. Or sorry, when you have capacitance and when you have just pure Faradaic current. But then when I go online and kind of look at some pictures, images of people using the Dunn method, and let me just, I'll share this again once I find the window. So when I share this, it looks like, and maybe it's not like I see these graphs where it's just like, oh, like this is the Faradaic and this is Faradaic plus capacitive or something. I feel like I see a lot of these pictures with like huge double layer capacitances, and they're changing a lot of things around. And that, in a way, I just don't know enough about the Dunn method. I don't know. Maybe it is only useful for just like supercapacitors or battery materials for elucidating capacitive and Faradaic processes. So I'm actually just kind of I don't know enough about the Dunn method. I just don't know if I necessarily believe it. I'm like, I've added all these like, if you want to do this, the best way is, if you want to look at it, like we have simulation software, cyclic voltammetry simulation software, and you can go to there's a website, aftermathlive.com. You can just get like a 1-month trial or something, and you can just play just like I did. I just played with the voltammogram to try to look at what happens when I have capacitive current, or if I have a lot of capacitance or not a lot of capacitance. How does that change the voltammogram? And you'll find that like, oh, capacitance, depending on all these other variables, it does a little bit in some cases, but there are other elements that play a role in what your voltammogram looks like, and what's the capacitive current and what's not the capacitive current. Especially when you look at like the scan rate as well. So I might use that to look at it, but in all my time doing electrochemistry, I rarely heard of the Dunn method for extrapolating capacitive current from your cyclic voltammograms. So, Umar, I don't know if that was helpful or not, but hopefully that does help at least a little bit.
Yeah, sorry, I can't be more help. I am not at all familiar with that.
Yeah, like
I do think more. I mean, based on what Alex just mentioned, I mean, you'd say it's not fitting properly. You know, it's certainly needs to be considered that the application of the method is not applicable to you, and that may be why it's not fitting. Yeah. But other than that, I don't have any other specific details. I'm just not familiar with it.
Yeah.
Yogesh says, I'm planning to do EIS measurements for metal air batteries. Can you give me some tips for 2 electrode systems? I mean, I don't know if you mean like tips for just like the experiments itself or like what to use for your battery exactly. Let me think. I mean, if you're doing so, yeah, for 2 electrode systems, I mean, the simplest sort of, I don't know, procedural kinds of things are you're going to want to connect the potentiostat working electrode to the cathode and the reference and counter leads to the anode. That's the typical configuration. You should have a positive voltage when you do that in your battery. And then, I'm not the most familiar with metal air batteries. My expertise is in lithium ion. But that being said, most batteries tend to follow a similar kind of pattern, which is that they do not. They have very low resistances and very high capacitances, and as such, they do not require high frequencies. So you might be able to start at like 10 kilohertz instead of a megahertz, for example, except for like solid state systems. But I don't believe that's a metal air battery per se. So you might only need to go moderately high, not really that high at all, as your maximum frequency to probe the batteries. And then the general I don't know, advice or just when you're doing impedance on a 2 electrode system, you are necessarily getting information from both electrodes. That sounds perhaps obvious, but in comparison to a 3 electrode system, if you were doing impedance with a reference electrode, for example, and you used the cathode as your working electrode, you would not be investigating the anode and its impedance. Doing a 3 electrode experiment means you are necessarily not probing the behavior of your counter electrode. But doing a 2 electrode system means you are. So in some ways that's a benefit, in some ways it's a detriment, right? Depends on what you're looking at. If you are just trying to study the properties of the battery somewhat as a whole and kind of try to look at both the anode and the cathode and how they're behaving, as long as you can differentiate between the two. And the typical rule of thumb for batteries, though I don't 100% know if this is the same for metal air, but for a lot of other kinds of batteries like sodium or lithium ion, for example, typically the higher frequency, lower impedance features are related to the anode, and the higher impedance, lower frequency features are related to the cathode. So in that way, sometimes you can differentiate in your impedance spectra which features are related to which electrode. The downside to this 2 electrode setup would be if you're looking to just primarily study one of them, like the cathode by itself, you physically cannot without a reference electrode. You will be impacted by the behavior at the anode as well. So again, whether you want that or not is for sure you can answer that. But it's just something to be aware of, right? You will get information from both electrodes in a 2 electrode setup when you do impedance. So, I mean, that's I don't know, the most general, I suppose I can try to give you on 2 electrode impedance. If you have more specific questions related to your setup, please feel free to ask. But that's about what I could give you therein, I suppose.
There was a follow-up from Umar. See, this is okay. What is the difference between, I need to ask, ESR, which is
series resistance?
Series resistance.
Okay.
RCT, charge transfer resistance, and Warburg impedance. Can you talk about the main difference between these? They all, in a way, represent some different things. The series resistance is also referred to as the solution resistance in some cases, the uncompensated resistance. This is resistance that's between your, I mean, really, hold on,
IR drop.
the IR drop, but I think it's easiest, right? If we just like
Draw thing.
draw things,
Yep.
we can draw things to make this. Oops, to make this. I just want to make sure thing is yep. Okay, last tool.
I'm gonna hide the question so we can see.
Yeah. So if you have like, let's just say this is your reference. I'm thinking about a 3 electrode setup. Reference, you have your series resistance. So that's your, I guess, ESR. I haven't heard of that phrase before.
Yeah, I'm not. Yeah, R sub 0 or R sub ohm, R sub S also are sometimes used just for what it's worth. So
now you have sometimes drawn
yeah, sometimes it's
a
by itself.
Warburg.
Sometimes it's in series.
Yes. So it would, let me make this a little easier.
It's more common to draw it the way you're about to.
So it's this and then Warburg.
Yeah, that's the most common.
Yeah. And then just say working.
Yeah.
Yeah. So and then just kind of putting
Counter.
things. So this is R
RCT.
CT Warburg it's T. No.
It's a specialty.
Very specialty.
Yeah.
That kind of bothers me a little bit. All right, let's just make it a little smaller. T. And then CDL, which you didn't ask about, but it's kind of part of the picture. Like this is how we picture and think about the electrode interface. Like all of this kind of represents impedance associated with the electrode interface. The ESR is the solution resistance, which is it's just the solution resistance. It's resistance associated with the electrolyte that is what we call uncompensated in some ways, because as a scientist, you're interested in applying a potential between this point and this point, but physically you have to have a reference electrode somewhere that can't actually be there. There's always some resistance associated with it. So that's what the series resistance is. And Neil has also mentioned that the series resistance might incorporate other things like resistances in cell cables and things like that. The RCT is the charge transfer resistance. It's the resistance, it's the Faradaic process when you're oxidizing or reducing some kind of species. And the charge transfer resistance is in many ways is a function of the potential that's being applied. So if the potential is very close to the thermodynamic potential of the species that you're oxidizing and reducing, RCT gets lower because more current is able to flow. It goes through this path, and all current that goes through this path is what's known as it's a Faradaic current. That process also changes the diffusion layer thickness, which is described by this Warburg element. And so because you have a change in the composition of solution near the electrode, there is an impedance that's associated with it. And the Warburg element describes that impedance. And that only happens if there's an electron transfer. So it makes sense that only that these two impedances are in series with each other. You don't get Warburg by going through charging the electrical double layer. You only have Warburg once you have an electron that's oxidized to reduce something through RCT, and then there's the diffusion layer thickness type of stuff. So that's like a brief explanation of these three things. These kind of I don't want to use the highlighter. I want to use the highlighter of like this guy, and this guy. So that hopefully these kind of helps you understand, and when you're circuit fitting, you draw something like that and look for that kind of data. Okay.
It looks like Rentaro asked, why does the rotation in an RDE drive the flux of bulk solution toward the electrode? Is it due to the vortex? Yes. Effect. I mean, I don't know if I can explain this.
It's a hydrodynamics.
Yeah, from a fluid dynamics perspective.
Yeah.
I'm not sure exactly how to explain it. It's more, this is one of these things that like I just did a webinar yesterday talking about RDE. And when I get to the part in the webinar where I basically say, okay, so we rotate the electrode, right? We have our electrode and we rotate it. And what happens is the solution is drawn up towards the electrode and then it, flows out and you get this kind of pattern. I have never actually thought to explain why. It's just like it's like self-evident, right? When you start, like, you can do this. It's like, what, if you have a cup at home, right? You just have a cup with some water, right? And then you take a spoon. That's a spoon.
It's a good spoon.
And you stir it around, the solution will start to twist around and move, right? Like you can just do this at home.
Yeah.
Right. I mean, it's a similar phenomenon. It's like there's the fundamentals of fluid dynamics is that the flow goes towards the object that's rotating. So I mean, the answer to your question is like, yes, the vortex, right? The rotation in and of itself causes a vortex like this. I don't know. Actually, I took a fluid dynamics class when I was in college, and I probably have to revisit some of that. I don't know if you use like Bernoulli's equation, or there's some equations of fluid flows, right, that you could probably use to describe that. But yeah, I mean, that part of the RDE, whole experiment basically is not electrochemistry, right? It's just fluid dynamics.
Yeah.
And it's laminar by virtue of like the Reynolds number that you get, for example, when you do the mathematics with this fluid dynamics, which is what like Levitch and did all these years ago when he developed the Levitch equation and characteristics of diffusion. It was assuming laminar flow, because if you rotate a certain speed, it causes a fluid dynamics to happen. And then the Reynolds number, which is dV rho over mu, when you calculate that using the diameter of the electrode, the velocity of the fluid, the density, and the viscosity of the solution, and for typical water, you end up with a number that's under 2000, and so it's laminar flow. That's literally just it. It's just fluid dynamics, right? And so because it's laminar flow, it allows you to do all this stuff. Basically, it's like all of the RDE stuff falls apart if you have turbulent flow or transitional flow. So it's like self-evident fluid dynamics. Like we're completely taking it for granted is kind of the point. So I mean, your question's a good one because you're thinking about the fluid dynamics, and to that point, when or if those fluid dynamics are not being observed or satisfied, your RDE experiments and data will be compromised. You won't be able to get proper Levitch, Kötecki-Levitch, or Tafel analysis, because it does require, the proper fluid flows and laminar flow. Sometimes when you rotate too fast, or you have a cell of a poor design, or it's, you get some kind of strange flow patterns, you won't have a laminar flow, proper, diffusion layer boundary and all this kind of stuff. And then you won't be able to really do proper RDE data. So that's true. Also, if you don't rotate fast enough, you won't have flow as well. There's
so
no flow, exactly.
There's definitely there's a lot of like theoretical stuff. Like if you had a theoretically perfectly like smooth cylinder with no like physical defects in it, you could rotate infinitely fast and all these types of things. But it's like now, when in reality you have all this other stuff that happens, that different problems come. Maybe this is a question for one of our mechanical engineers. They may remember why does rotating a cylinder cause flux to the...
Well, it's turbulent around the outside.
It's turbulent.
It's because the shear. That's because the shear is higher. That like the tangential or radial, whatever the right word is, speed around the outside of the cylinder is faster, and it's obviously bigger with the thicker the diameter of the shaft, right? The speed at which it's moving is faster, so that creates a higher shear and a higher force in the interaction. Whereas at the bottom of the electrode, especially as you go closer to the center, it's not moving as
Yeah.
much.
Oh,
And so the result of that is that it doesn't move the solution as much. It's less,
Yep.
there's less shear, and then the flow is laminar or something like that.
Yeah.
But yeah, I don't know.
Hopefully
I'm not sure
that
how to,
helps
I'm
you.
not, yeah, I mean, the better answer would be probably a long mathematical one to display some of that, but it's a little bit easier to just say that it's self-evident. It happens. the flow happens when you stir a thing and you get a solution, thrown at the electrode and yeah. So, but yeah, it is because of the vortex of the solution from the electrode.
Yeah.
Yes.
Okay. Going through.
Yeah. Back to discussions about guitars.
Oh yeah, go for it.
No, I don't have anything. I'm just teasing.
No, there's
Let's do our little podcast preview. And
Sure.
So
people are
what we're
watching.
gonna do now, everybody, is play you just a couple of minutes, maybe a minute and a half or so, of the first episode of the Electrochemistry podcast. And just as a little sneak preview, as we said at the opening of this, we've launched a podcast. It released yesterday, actually, on our YouTube channel to tier 2 members. It will be there for about a month until January 4th. Then it will be in all the places, Spotify and Apple, Google, whatever. But just as a teaser or whatever, I'm going to play you a couple of minutes of the first episode.
Mhm.
And if there are any other questions on electrochemistry, please feel free to type them. We'll answer. But if there aren't any questions, we will conclude at the end of this little sneak preview of our first podcast episode.
Mhm. Seriously, are we gonna get all huffy about this? Technically, they are hydronium ions.
Yeah, Alex, how many people know what a hydronium ion is?
Same number of people who know what a proton is.
Yeah, that's precisely 0 people.
Welcome to the Electrochemistry podcast, where we discuss all things electrochemistry. I'm your host, Dr. Alex Peroff, and with me is my co-host, Dr. Neil Spinner. On today's podcast, we'll be hearing a story about graduate student Lisa. Lisa had just finished her last set of classes she needed to take as a graduate student. The spring semester ended, and she had lots of plans to catch up on research over the summer. She was planning to do some new electrochemistry experiments, but had to perform a routine CV test on her glassy carbon electrode first. However, instead of getting a smooth voltammogram, her voltammogram contained jagged edges and sharp zigzagging and crisscrossing lines. Confused, Lisa took the electrode out of the cell, and while visually inspecting the electrode, Lisa looked in horror as her polished glassy carbon surface had black, jagged spikes protruding from the electrode. What happened to Lisa's electrode?
Whoa. Okay. Before we go any further, I have to tell you that I figured out what the problem is going to be. It's trying to get experiments done during the summertime. Okay. Go to the beach or like a barbecue. Starbucks has really nice summer drinks. Like, enjoy life.
Yeah, but I mean, like, after I finished graduate school classes, I was pretty eager to start doing research full time. Like, no more classes, just research. But I was so young, so naive. Neil, were you excited to do research once you finished all your classes for graduate school?
No. But then again, I'm not young, naive, or apparently someone who has a good work ethic, apparently. Who's young, naive, or has a good work ethic.
Yeah.
That's
yeah.
right. There you go. Okay. Anyway, if for those of you who are watching with us still, hopefully that was a little goofy, fun preview there. So there's some other fun little snippets, some fake advertisements and games, and we do all kinds of goofy, fun stuff. It's not meant to be as educational as this live stream, for example. So I do hope that you all check out our podcast at some point if you have the time and the interest, and if you want to wait until it's available on all your podcast locations too in January, that's fine with us as well. We do appreciate anybody listening to our stuff and joining us. So I suppose we'll wrap it up here.
All right.
Does that sound good?
Let's do that. I think that sounds good.
So keep in touch with our YouTube channel. Like we said, we have a company function next Friday, but perhaps we'll do this earlier in the day or perhaps not at all.
Yeah.
It's not clear, but there will be an event, scheduled on our YouTube channel if we're doing one, right?
Yeah.
So check that out. And I guess if either of us don't see anybody or talk to anybody for the rest of the year, have a happy holiday season, I
Yeah,
suppose.
that's right.
And a happy new year, and I don't know, all of that good stuff, right? So,
Yeah.
all right, take care, everybody.
All right.